Okay, in this video, I would like to talk about the shear strain in relation or definition of shear strain in relation to the cross-sectional rotation as well as the slope at the point that we are considering the cross-section. And this is in addition to the uh, uh, discussion that we had in previous videos on this topic. Uh, the objective of this video to introduce a more general and, shall we say, more independent in terms of sign convention or coordinate system requirements for defining these quantities. This applies to both Timoshenko and Euler beam theory. I came up with this approach for two reasons. One, I find out that in several resources and references, the treatment of these quantities, specifically definition of shear strain and in relation to other quantities involved, as I mentioned, are very case dependent. Sketches are drawn, and then based on that sketch and some definition of the coordinates affects the definition, and sometimes the sign convention becomes sometimes confusing. So I believe this approach that I am going through in this video helps resolve these issues and make it more, shall we say, unified or universal. The way that I'm going to approach this is as follows. As we had in previous cases, we have a beam, and I try to make it more than a kind of two-dimensional. And then we have a center line, which we usually say X goes through the centroid, and in our coordinates, we have the Z downward. Now, one thing that we discussed in the previous videos is this, that if I have a cross section at any location along the beam axis, if I have the cross section after beam is deflected, and I just draw the center line here, after beam is deflected, this cross section will be transferred in the Z direction, and then it will have some rotation. And in the Euler beam theory, we said that the normal of this rotated cross section always is aligned with the tangent at that point to the elastic curve, and in Timoshenko beam, that requirement is relaxed, and the cross section can have a different rotation by different amount of the different amount than 90 degrees that it is required for Euler Bernoulli. Okay, so how do we get these things? One thing is that we came and considered the tangent to the elastic curve, and then we had two quantities, and then we took care of it. But here I would like to use the rotation matrix which we covered in the first two videos. And the rotation of just a cross section. I will consider only the cross section here as highlighted here in orange, and say, okay, this cross section has at the initial thing has a normal, unit normal, and let's say n, and this unit normal vector has the component of 1, 0, and 0. Now, when this cross section rotates, then the normal also rotates with it. Let's say call it n prime with rotation. And this is what I'm after, this normal vector to the rotated cross section. So what I will do here, I will actively by actively I mean the rotation is active. That is, we fix the coordinate system xz here, and we rotate n in that coordinate system. Actively rotate the cross section by phi. This phi so far has no connection to the rotation of the cross section in Timoshenko, but we will relate it to it. Just let's say it's a phi, as an angle. Therefore, I will get my rotation matrix becomes cosine phi, 0, sine phi, 0, 1, 0, minus sine phi, 0, cosine phi. So this is my active rotation matrix. Remember that when you use Rodriguez equation for a rotation matrix, here I am assuming that the rotation is positive. It doesn't matter, I will explain it later. But to have some convention here, I assume that this is positive. Therefore, my axis of rotation is an 0, 1, 0 about the axis, which is basically positive y direction. And therefore you get this matrix here, which is the active, which is the transpose of the passive rotation that you can get from Rodriguez equation. So the background for this is the early videos, video 1 and 2. Now I come and transfer my normal vector, initial normal vector, to my cross section, and that will give me cosine phi 0 minus sine phi. Okay. Again, I will come here and rotate the same cross section by theta. Independent angle. And similarly, I will get cosine theta, 0 sine theta, 0, 1, 0, minus sine theta, 0 cosine theta. And again, I will transform my initial normal vector or unit vector, and I will get cosine theta 0 minus sine theta. Note here that these are purely geometrical. I have not related these two rotations to any beam mechanics yet. And these are two different rotations that we apply to this initially perpendicular cross section to the unit normal along the x-axis. Now, I come here and say, okay, let's find the angle between two new normal vectors. Because here I have said that my initial cross section, maybe I use the same color so we connect these concepts together. I have my initial vector as shown in the initial direction, and then let's say it rotates, and therefore it will have a normal. Similarly, this is by phi. Similarly here, I have the same cross section and rotate it, and then I have a different normal vector because this is theta. Now I want to find the orientation of these two normal vectors as given here. These are the two vectors, and I want to find the angle between these two. Therefore, I will use using dot product operation. Okay, so what happens here, I will write the cosine phi 0 minus sine phi transpose times cosine theta 0 minus sine theta, and that will give me cosine phi cosine theta plus sine phi sine theta. So the dot product of these two, the first component and second component and third component, multiplied by each other respectively, and therefore I get this. From trigonometric identity, we can write this as cosine phi minus theta. And that is a very important result. Although the operation, as you see here, I have not used any. By the way, if you use, I just to be consistent between these two, I just use positive rotation. If you do the same thing for negative rotation about the negative y, you will get the same result here. And even more beautifully, even if you use passive rotation, you will get the same result. Although here, from a mechanics of beams, we would like to use active because we keep the coordinate system fixed and we calculate the deflection and rotation based on that coordinates. And this is very important for generality, but you will get the same results. So let's result cosine phi minus theta. This is the angle, because when you these two vectors are unit vectors, because their magnitude is 1, and therefore when I multiply use the dot product, I will get the magnitude, which is 1, and then times the cosine of these two. So this is the angle. Therefore, y minus theta is the angle between normals or unit normals. Let's call this angle gamma. Now, realize here that if y is equal to theta, gamma is 0. And this is, I will mention how these two are connected to each other, to the beam mechanics. You see here that we are recovering Euler-Bernoulli easily, because Euler-Bernoulli doesn't consider shear. Shear deformation is absent in that theory, and that is exactly when the two rotations that we have here are equal, and because one of them is perpendicular, therefore we get always the perpendicular cross section all the way after rotation. Now, how do we connect these things to the beam mechanics? So relation or connection to beam mechanics. If I come here, as you remember, probably if I say ui, the displacement is u0w, and then we had u is y, z. In the cross section, u is the x component, and w is wx, if you recall in Timoshenko. Now, if I come and calculate gamma xz, the shear strain component is du dz plus dw dx, which is du dz is phi, and dwx is dw dx, because w is only function of z. But we know that this quantity is minus theta. You remember that we had theta is minus dw dx. And if you now write gamma xz in terms of theta, would be phi minus theta. And now compare this to this purely geometrical relation that we got here. And you see that these two are exactly the same quantity. So therefore, we can say that gamma is our angle between the two normals, is actually gamma z, xz actually. And that connects beautifully this geometrical treatment here that we had, the two normals, with the kinematics of Timoshenko beam, as well as for the case that these two are equal, the shear is 0 of the Euler-Bernoulli beam kinematics. Now, one more thing that you may want to add, I may want to add here, and that is if you write this cosine as sine pi over 2 minus pi minus theta, then you see that this is actually the deviation from normality. And that is another definition that we give for shear strain, that because here we have normal angle, any deviation from normality is shear by definition. And we know that the normality is maintained in order Bernoulli, therefore shear is 0. But clearly we see here that the normality is measured with this angle. So if this quantity is 0 or otherwise gamma is 0, phi is equal to theta, therefore normality maintains and this equality maintains. Otherwise, any amount that deviates from normal pi over 2 angle, say, is the shear, as we discussed. So I think this, I believe actually that this simple treatment, you see that I didn't need to use, except for consistency. You could say here that, okay, rotate this vector initial normal by counterclockwise, clockwise, and be consistent in your operation, you will get exactly the same results. So no sign convention ambiguity, no dependency on the coordinates. We beautifully with this treatment and just dealing with one quantity. I didn't go into the complication of tangent to the elastic curve in relation to this. I just use this cross section and it's normal to come up with the definition of the shear strain, as you saw here. So I hope this a little bit clarifies more, at least, for this relationship that we have for gamma, the shear strain in relation to the rotation of the cross section, as well as the slope at that location, theta, or dw dx. Thank you.